Hello again, and welcome back to my computer vision series. Today we'll talk about vision transformer and its impact on the entire field. This is the plan for today. So first we'll start with a small overview of the model, of the scale, the cost of the compute that was required to train a huge model like that. Then we will discuss a little bit of philosophy behind the model, what the authors mean by inductive bias, and why we think it's really important to understand stuff like that to really get deep learning. Finally, we will go through model architecture, so how the model actually works, and then see some results. And let's start with model overview. So first of all, I have a bunch of videos on my channel about object detection. That was my focus in recent month. And we've seen the old style model using convolutions called YOLO, which is quite popular at the moment. We've seen the novel transformer-based object detection detector called DATR, which is in some ways clean and really cool, but then it didn't have that good quality. We've seen some improvements on top of that, like deformable data, DAP data, denoising data, that helped improve it a little bit, but still not quite the same as old school convolution-based models. But then all of these models still used ResNet 50 as a backbone. So they started image processing with applying ResNet 50, and then they had some transformer heads on top of that. And turns out that when you replace this ResNet 50 backbone, this old style convolution backbone, with transformers and something bigger and more powerful, you can get insanely good results. So today we are looking at vision transformer. So this is the first such backbone which solves image recognition task, image classification. There is another one that we'll hopefully talk about soon, the swing transformer. And for the actual object detection, Dino model used swing transformer as a backbone, and it was state-of-the-art in model detection, in object detection for quite some time. And current state-of-the-art called CoDator, it tried out both swing and vision transformer as a backbone, and it turns out it actually works better with vision transformer, and that's like insanely huge difference with the old school object detectors like YOLO. So first of all, a little bit of overview of dataset sizes. So when we were talking about object detection, we mostly talked about COCO dataset. So models like YOLO just train on COCO dataset from scratch. So they don't use any pre-training, any downloaded weights, just take this small dataset, train on that, and that's enough to do object detection. Models like DATR also have a backbone. So in case of DATR, that was ResNet 50. That was trained on ImageNet 1K dataset. So this is the famous challenge that basically was a proof of concept of deep learning for image recognition. And so COCO dataset is only 20 GB, and then ResNet is 150 GB, which means that it is something you can play around yourself. You can download it to your computer. You can train models in just a few days on a modern GPU, so it doesn't require a lot of compute. You can do it yourself. Then ImageNet 1K, that's 1000 classes subset of the entire ImageNet database. And the entire database has 21K classes. It is roughly 10 times bigger than ImageNet 1K. So that's 1.3 terabytes of data. And then the vision transformer that we are talking about today, that was trained by Google, it was trained on a dataset called JFT, which is not available open source. You cannot get access to it. You can only work with it if you work at Google. And this is 30 times bigger. So it's insanely huge data set to add some time and money to this understanding. Right? So you can train something on Coco dataset and ImageNet 1K in maybe 1 week on just one machine. And if you don't have a GPU at home, you can rent it from Google Cloud, and for a week that might cost around $50 for a simple GPU. Now, Vision Transformer that is described in the paper took 2,500 TPU days. So it's 10 years of one TPU, or 1 year of 10 TPUs, or 1 month of 100 TPUs. So that's a lot. And if you actually compute the cost of that, so they have cost per hour listed on the Google Cloud website. If you would rent TPU like that, that comes up to around $60K. So that's quite a lot, and that's just one launch. I imagine that to actually write a paper like that, to do proper research, you need a lot of hyperparameter tuning. You will have bugs that you solve, and then the entire training is useless. And you would have a lot of architecture search. So the paper itself probably costs at least $1 million of GPU of compute just to train the models. And that's not counting actually collecting the data set, actually storing it, and all of that. So this stuff like that is only available for big tech companies like Google, maybe Facebook. It's really getting harder to work at such scale for everyone else. So now let's talk about philosophy behind Vision Transformer and what authors mean by inductive bias. So I'm just going to show just one slide from the original paper. This is the paper that introduced Vision Transformer. And so the question is, let's say we have 100 times more data, 100 times more compute. How do we use that most effectively? So before that, in computer vision, a lot was based on convolutions. So naturally, the first thing to try was to just take effective model that we know has good architecture, like ResNet 50, and just try to scale it up. And that's actually what this research group from Google did before trying transformers. And we can see results here. So they have another paper called ViT, which basically takes ResNet and tries to make it much, much bigger. So it's also a huge project. They also use the same GFT dataset, thousands of days of TPU compute. And it turns out that although convolutions do help when models are small, when you don't have a lot of data, once you have a lot of data, at some point transformers begin to do better. And the fundamental reason for that, we believe, is the so-called inductive bias. So what is inductive bias? First of all, the first time anyone talks about convolutions, we always mention that convolutions are supposed to be good because they conform to some of our expectations about how an image recognition system should work. And so convolutions have these two properties, so the translation equivariance and locality. So translation equivariance basically means that if an object is there and then it moved over here, it is still the same object. And we believe that to be helpful because this is how we see objects in real life. We move around, we look at the objects from different angles. So any system that will do the same should have that. Second one, locality, is basically saying that if the object is over here, to recognize it, to detect this object, to understand what's going on here, it is more important to look at pixels that are nearby, that are close to the object, that belong to that object, instead of something that is over here. And that might be useful, but maybe not for all the cases. And here's one such example where that might not actually be useful. So imagine that you want to recognize road signs. And a lot of modern cars actually know how to do that. So they have a camera. Every time you drive around, it will just automatically recognize road signs and then just display them in your HUD, or maybe just adjust the speed of the car depending on that, and so on. So it is true that, to understand that this is a road sign that says 20 miles per hour, you actually need to look at that location. Although that's not entirely true, because if you just crop it out, or if you put the same road sign into some unexpected location, it might actually be harder for people to recognize it, because a lot of information about the object we actually get from the context. And so just looking at this picture, we immediately see that it's a road, it's a street, and so this probably is a road sign, so it does help. In addition to that, we are not just interested in understanding that that's a road sign. We also need to know if this road sign is applicable to us. And in this case, we can see that we seem to be following along this road, and this is where the road goes. But also here is another road that seems to be just a turn of the main road. And then this sign seems to be standing here. So it's probably is applicable to this road, not to this one. And so it is not applicable to me. And for that sort of reasoning, it takes a lot of non-local communication. So we're looking here, we understand that this is a road, we're looking at different areas here to understand that this is the road we follow, and then this is a different road. So it's a lot of areas within the picture that can be quite far from one another, that have to communicate with each other. And so if you remember how convolutions work, so if you have an input picture, the 1 pixel in the output picture of one layer will basically consist of some weighted information of 3x3 matrix in the input image. And then if you have a couple of layers, then this effective receptive field starts to get bigger and bigger and bigger. So eventually it is true that if you have deep enough network, that different pixels do communicate with each other. But there are some problems with that. So first of all, if the network is limited in depth, you'd only have like 1, 2, 3 steps of this interaction, because every interaction now takes a lot of layers if you want areas from the opposite side of the picture to communicate with each other. And in addition to that, because it takes a lot of layers, by the time the signal actually gets to the other side, a lot has happened. So the signal is becoming noisy, it is becoming stale. In contrast, in transformers, we don't have that. So in transformers, we have fully pairwise interaction between all the elements in the sequence. So we have this one-to-one interaction between every area in the picture, in every layer. And so if you have 12 layers in the model, you will have 12 steps where each area can effectively interact with every other area. So this is really good in this sort of area-to-area interaction. So to sum up, transformers, we believe, to be a more effective architecture in general. So a lot of people call it just generic differentiable computer that is able and effective enough in all sorts of tasks. And by now, I think it has been proven by time that, at least from the architectures we are aware of, transformers seem to be the best in so many cases. Transformers do not have inductive bias. And what that means is that these biases that we've talked about, the translation equivariance, the locality, they might be useful for the majority of cases, but not for everything. Which means that if you don't have that, you will need to train for a longer time. You will need to see more data so that the model can understand and basically learn the same thing. Now, the good thing about that is that the model will learn when to use that and when to not use that. So in some cases, maybe these biases are harmful, And so the model will be able to understand that and to train differently to be able to deal with the situation. Okay, so we get it. We have a lot of data, a lot of compute. We need to train transformers. Now, how do we do that? Historically, a lot of people thought about that, but it's not really clear how to do that. And the main problem is the time complexity of the transformer. So the transformer receives an input sequence of elements, and the time complexity of that of the transformer is quadratic to the sequence length. Which means that for 2D images, when we just flatten out the input and pass it to the transformer, now the complexity becomes quartic, so that's fourth power, depending on the edge size. So for images with high enough resolution, there's just too many pairwise interactions between every individual pixel to be viable. So it is prohibitively expensive to just take pixel-wise transformer and apply it to a high resolution image. And so in Vision Transformer, that is solved by patching. So we start here. So we have an image and we divide that into a certain set of patches. So here it is depicted as 3 by 3, but usually they do something like 16 by 16. So we have these patches, non-intersecting pieces of the image. We pass each of them through the same dense layer to project that to a increased hidden dimension, and then we flatten it all out. So we had 16 by 16 patches, we flatten them out, so we get sequence of length 256, which is totally fine for a transformer. Obviously, since we have lost the positional information after flattening, we also need positional embedding. And the authors say that they actually tried 2D positional embedding and 1D positional embedding and didn't see any difference. So they just train one-dimensional learnable positional embedding. It is learnable, it is not sine cosine because there's just so much data that it is going to learn what it needs to learn. And it's quite curious that the embedding itself is one-dimensional, which means that it just learns the index of this patch. So it doesn't know that this square is located under this square, but as we see later, it actually can learn that implicitly from the data. And this is something that it just learns on itself. And so we have this projected flattened tokens, we add position embedding to that, and then we just pass that through the transformer. And as we know, the output of the transformer is always of the same shape as the input. And so we need to perform our task somehow for the actual image classification. And so to do that, we actually just take the first token. So we always say that the first token in the output is in some way special. So even though we had 256 output tokens, we throw most of them away and just take the first one. In doing that, authors also found out that it is useful to add an extra token to the input, and it is called the special class token, which will correspond to this output token as well. So instead of just having this 256 image tokens that correspond to a specific patch, we also add a special token that corresponds to class, although that is just trainable vector of parameters, basically. It does not depend on anything, but it turns out having this extra token in the input sequence is helpful to the transformer, so it can put some actual class-related information into there, and it can understand that this is the specific, should I call it, piece of memory to store information you need for the actual classification. So let's go over all of this one more time. So JFT is similar to ImageNet, and to train that, we actually use fixed size images of 224 by 224 pixels. We split it into 16 by 16 patches. So every patch is going to be 14 by 14 pixels, because 14 times 16 is 224. Each patch will be passed through the same dense layer to project it down to just some certain hidden size, like 168, for example. Then all that output is flattened, so we get 256 tokens, each token representing this embedding that came out of the dense layer. In addition, we add learnable class token as the special token that can be used as just a piece of memory for the transformer that does not correspond to any part of the image, to just store information that is relevant to the entire image itself, like the class of that image, for example. And so the transformer receives 157 tokens in the input. The output of that is also 157 tokens. And we just take the first one, pass that through some more dense layers to get the actual class predictions. Another interesting part is inference. So even though we train on fixed size images, we might want to perform inference later on images of different size. The patching operation is actually a special case of just a convolution. So it's a convolution with the kernel size being equal to stride. So it's actually how it is written in code. And that one doesn't care about image size. So if you enlarge the image or if you make it smaller, the number of output patches changes, but the process is still the same. Transformer also doesn't care about the actual size of the sequence. So it doesn't see the whole sequence, it just computes all the pairwise interactions. And so you can feed in variable sequence sizes, and the transformer can deal with that and will not even notice anything. The only thing that actually does depend on image size is the positional embedding, because we had 16 by 16 embedding for position, which is trained, and it's trained to provide some information to every specific position. And so if you just naively resize that, that information will become weird. So to deal with that, we basically do the same thing as our computers and phones do when we just zoom in on the image. The positional embedding is resized to the size that we need it to, using bilinear interpolation. So basically we use this old trained 16 by 16 embedding as a set of reference points. Then we resize the image to the size we need. It can be smaller, it can be bigger. And then we find out the value that we need to put in every pixel in this resized picture for the position embedding based on 4 nearest values of the original embedding. So this is exactly the same as you would compute pixel values if you were to resize the image itself. And that's quite cool to use the same technique, but not for image, but for embedding, and it still works the same way. So this was it regarding the actual model architecture. This is one of the things we like about transformers, that they are so uncomplicated. Really, the architecture is the same from model to model, from task to task, from NLP to image recognition, and so on. You just need to come up with a way to actually create the sequence to pass into the transformer. Now let's talk about results. Vision transformers come in many sizes. So the smallest of them is pretty much the same size and inference cost as Resident 50, and still it overtakes Resident 50 on ImageNet quality in terms of top 1 accuracy, and it gets about plus 3%. But also there is ViT large, ViT huge. So the huge one is roughly 10 times the size and the inference cost, and it improves accuracy by a lot. To understand that it's not just, this huge thing that is unusable in real-time circumstances. Here is the graph. So to the left is the actual number of images per second that you can get from a GPU. And so we can see here that for a classical ResNet 50 and a similar size model of Vision Transformer base, these two lines are pretty much equal. So Vision Transformer in this size variant can be, the inference can be performed with the same speed as for ResNet. The quality is slightly higher. And we can also see that the speed does not really degrade that much with image size, meaning that this quadratic transformer sequence length dependency does not really yet kick in, even at high enough image sizes. And the bigger vision transformers, like the huge variant, they are obviously roughly 10 times slower. When added as a backbone to our favorite object detectors, they give roughly 10% multi-average precision on COCO dataset, which is really a lot. This is probably the main thing that allowed transformer-based models to overtake classical convolution-based approaches in object detection. Apart from that, Vision Transformer is used in a variety of other applications, sometimes as just a good model on its own, sometimes as a backbone for initial image processing to be used by some other models like segmentation and so on. And here are just some interesting slides about what is actually going on inside the model. So this one is for this first dense layer that is used for this 14 by 14 pixel patch projection. And this is just the representation of a input feature map that maximizes the output of specific pixel. And we can see here that they actually look really, really similar to similar visualizations of convolutions. So this dense layer, even though it does not have translation symmetry, it does not have locality, it still manages to learn to recognize patterns like edges, ridges, circles, grids, color gradients, all of that. Simply because there's so much data that, even the dense layer can manage to do that. This is the visualization on what is happening with this one-dimensional positional embedding, and it shows just the similarity of the embedding for different coordinates of the patch. And again, we see that despite the fact that we did not explicitly provide this 2D information to our embedding, it pretty much learned that the index number 1 is located somewhere in the upper left corner, and then it basically shifts to the right. So it got pretty good idea to understand like where current patch is located, even though this 2D information was not explicitly put in the model. And this one is a representation of attention distance of interactions between different tokens. So you can imagine that for ResNet, that will be something like this. So it's always a distance of up to 2 pixels. So that's quite short. But then if you have a large enough network, a deep enough network, if you compute the cumulative distance that you get from many layers, it starts to go up, though it is not as effective as just communicating within the same layer. And we can see that from the very first layer, some attention heads already look really, really far in the picture, even though they just look at pretty much raw pixels at this point. And a lot of them do indeed focus on localized information. But then after just a few layers, the network mostly focuses on long distance relationships, which means that it already knows everything there is to know about the current location. So it does not need to keep focusing on the same location, and instead just argues around the image as a whole and gets a better understanding of what is going on. And this really showcases why transformers can be more effective at that task, because this sort of long-range interaction and many steps of interaction will take insanely deep convolutional neural networks. With transformers, we don't have to go so deep, so transformers tend to be more effective in that. So that was it regarding the actual vision transformer. I want to remind you that I have my channel. I have been focusing on image recognition and object detection a lot recently. So I have the whole series about modern object detection, starting with vanilla, old school convolution style object detector called YOLO, which is really lightweight, quite performant, quite accurate. Then we've discussed the data model, which is a foundation for a lot of models that came after that are cleaner in some aspects, that have opportunity to have better quality. We've discussed how to improve that. We've discussed deformable data, DAB data, denoising data. Today we've discussed vision transformer. And the very next one will be about reading vision transformer source code so that we can basically clarify some details about the implementation. Although it is quite easy, at least the model architecture itself. Training code obviously will be much harder with a lot of stuff going on. In addition to that, I'm planning to do a video about shifted windows transformer, this WIN, that then is used by a famous model called Dino for object detection, which was state of the art for quite some time. And then the next one, which is current state of the art, is codator, and I'm also going to talk about that. So we have a lot of ground to cover. See you soon.